On the 14th of May 1973, NASA sent Skylab into space, marking the United States' first orbital space station. Only 63 seconds after liftoff, something went wrong. The micrometeoroid protection layer tore loose, and with it, one of the station's solar arrays was damaged. The situation worsened once Skylab entered orbit. That protective outer layer had not only been shielding impacts, it also served as a barrier against solar heating. Without it, a large exposed section of metal was directly facing the sun. Heat built up rapidly, and internal temperatures rose beyond 130 degrees Fahrenheit, equal to 54 degrees Celsius. Supplies began to degrade. Food was spoiling, film stock was melting. Certain plastic insulation materials risked releasing harmful fumes. At that point, NASA had a multi-billion-dollar station effectively turning into an orbital furnace, drifting roughly 270 miles above Earth. The question became urgent. What could be done? Installing a conventional cooling system was impossible. There was not enough electrical capacity, and no way to deliver heavy equipment into orbit on short notice. Instead, engineers moved fast and designed a surprisingly simple fix in just 11 days. They created a deployable sun shield. It was a foldable parasol constructed from nylon, mylar, and aluminum layers. The crew extended it through an airlock and opened it above the damaged area, forming a shaded barrier, much like a beach umbrella. Within a short period, internal conditions dropped back to about 75 degrees Fahrenheit, around 24 degrees Celsius. There was no compressor, no coolant loop, and no electrical refrigeration involved. Only direct application of physical principles made the difference. That recovery demonstrated a deeper lesson often overlooked in cooling technology. The most effective thermal control systems ever developed do not rely on powered air conditioning. Instead, they depend on radiation control, reflection of solar energy, evaporation processes, and changes of state in materials. Over decades, NASA refined these approaches because space does not allow traditional cooling units. Much of this work was funded through public resources and documented in technical archives and spin-off records that remain accessible but are rarely studied. Meanwhile, households continue relying on standard compressor-based air conditioning systems designed in the 1800s, paying significant electricity costs every summer. Today, 7 NASA-inspired cooling methods are being examined, each rooted in space engineering, along with how they can be applied in everyday environments at relatively low cost. The final method is especially unusual, originally developed to sustain astronauts on the lunar surface, where sunlight can push temperatures to 250 degrees Fahrenheit, or 121 degrees Celsius, and it can now be replicated for roughly $40. The first method is the same principle that saved Skylab: external shading. At first glance, it appears too simple to matter, which is why it is often misused. NASA engineers understood a key rule. Heat must be blocked before it enters a structure, not after it has already been absorbed. When sunlight strikes a roof or wall, that material absorbs energy and later releases it inward over time. Closing interior blinds does little at that point because the heat has already passed through the building envelope. The Skylab parasol worked because it was positioned above the damaged surface with an air gap between layers. It intercepted solar radiation before it could strike the metal, while allowing heat in the gap to dissipate into surrounding space. This same concept can be reproduced in practical settings. A suspended shade sail or simple tarp placed 12 to 18 inches above a roof, tent, or mobile shelter creates a similar buffer zone. The upper layer absorbs solar load, and moving air in the gap carries heat away before it reaches the interior. People who use this approach often report indoor temperature reductions of 10 to 20 degrees Fahrenheit, or 5 to 11 degrees Celsius, compared with unshaded surfaces. A durable shade sail typically costs between $30 and $80. The Skylab system, by comparison, required millions to implement in space. The second technique traces back to 1964. NASA needed a way to handle extreme thermal swings in spacecraft exposed to both intense sunlight and deep shadow. Engineers at the Marshall Space Flight Center developed a thin plastic film coated with an ultrafine layer of vapor-deposited aluminum. This material became widely known as the space blanket, the reflective silver sheet commonly found in emergency kits. It is capable of reflecting up to 97% of radiant heat and is recognized as one of NASA's most successful technology transfers into civilian use. Here is why that matters for cooling. On a summer afternoon, the underside of a standard shingle roof can climb beyond 150 degrees Fahrenheit, or 65 degrees Celsius, and it pushes that heat downward into attic space and living areas like a giant heating element. Insulation slows the transfer, but radiant barriers act differently. A layer of perforated aluminized foil fixed under rafters, with the reflective side oriented toward the attic air gap, sends radiant heat back upward through the roof structure. The United States Department of Energy reports that radiant barriers may reduce cooling energy use by 5% to 10% in hot and sunny regions. At the same time, attic air temperatures can fall by roughly 30 degrees Fahrenheit, or 17 degrees Celsius. Material pricing is about 15 to 25 cents per square foot. A small cabin roof can be covered for less than $100. The same physical principle is used in high-end systems that protect instruments like the James Webb Space Telescope. The third method becomes far more unusual because it generates cooling using only the sky itself. This is known as passive radiative cooling, and it is the primary way spacecraft release excess heat. In the vacuum of space, there are no fans or airflow. Heat can only leave through radiation into infrared wavelengths. NASA applies special coatings to radiator surfaces that emit thermal energy within a narrow infrared range between 8 and 13 microns. This range passes through Earth's atmosphere without significant absorption, and it is referred to as the sky window. Any surface emitting within this band effectively connects its heat transfer path to deep space, which exists at approximately negative 455 degrees Fahrenheit or negative 270 degrees Celsius. Deep space functions as an enormous heat sink that absorbs thermal energy without cost. In 2021, researchers at Purdue University extended this concept further. Working within the same scientific framework used in spacecraft thermal systems, they developed a barium sulfate-based paint that reflects about 98.1% of incoming sunlight while still emitting heat through the sky window. The Guinness World Records recognized it as the whitest paint ever produced. Field tests showed that coated surfaces were about 8 degrees Fahrenheit or 4.5 degrees Celsius cooler than surrounding air under direct midday sun, and up to 19 degrees Fahrenheit or 10.5 degrees Celsius cooler during nighttime conditions. The Purdue team estimated that 1,000 square feet of this coating can generate roughly 10 kilowatts of cooling capacity. That level exceeds the output of many residential central air conditioning systems, while consuming zero electrical power. Although large-scale commercial distribution is still in development, standard cool roof coatings operate on the same principle. These products reflect between 80% and 90% of sunlight and are available in hardware stores for about $30 to $50 per gallon. On dark roofing surfaces exposed to strong summer sun, such coatings can reduce surface temperatures by 50 degrees Fahrenheit or 28 degrees Celsius or more. This makes it one of the most effective low-cost upgrades for off-grid thermal control. An additional method extends this concept into nighttime cooling. A shallow, insulated panel filled with water tubing can be positioned to face the open sky after sunset. This is known as a night sky radiator. Under clear and dry conditions, heat from the water radiates upward through the sky window into space, allowing temperatures to drop below ambient nighttime air levels. In desert environments, this approach has been used for generations to cool water overnight and circulate it through living spaces during the day. The sky, in this sense, operates as a natural heat sink that functions like an open refrigeration system, though most people never make use of it. The fourth method originates from Mars exploration. When NASA's Jet Propulsion Laboratory sent the Sojourner rover to Mars in 1997, it had to survive nighttime temperatures near negative 100 degrees Fahrenheit or negative 73 degrees Celsius, while operating under an extremely limited power budget for heating. The solution was aerogel, a material originally created in 1931 by chemist Samuel Kistler and later refined for space applications by NASA. Aerogel is a silica structure in which nearly all liquid content has been replaced with gas. It is more than 99% air by volume, making it the lightest solid material known and one of the most effective thermal insulators ever developed. NASA researchers referred to it as frozen smoke due to its appearance. It was also used on the Stardust mission to capture comet particles traveling at hypersonic speeds without causing damage. The same material designed for Martian cold conditions has direct applications on Earth. Any insulation system that works in winter also restricts heat transfer in summer by preventing external heat from entering interior spaces. Aerogel is now produced in flexible blanket form for industrial pipe insulation, and surplus rolls or cut segments are sometimes available at reduced cost. A layer approximately 1/4 inch, about 6 millimeters thick, can provide insulation performance comparable to much thicker fiberglass materials. This approach is designed for extremely confined environments where standard insulation cannot be applied. It works in narrow structures such as van walls, window inserts, insulated containers, and compact tiny home roofing systems. Its key advantage is density of thermal resistance, delivering high performance and minimal thickness. The fifth method is concealed in everyday bedding materials, and its origin traces back to astronaut glove research. During the 1980s, NASA supported studies focused on protecting astronaut hands from extreme thermal shifts during spacewalks. The contracted research team developed microencapsulated phase change materials. These are microscopic capsules filled with a wax-like substance engineered to melt near skin temperature. The core principle is latent heat. When a substance changes phase, it absorbs large amounts of thermal energy without an increase in temperature. These capsules absorb excess body heat as they transition from solid to liquid, then release that stored heat when temperatures drop and they solidify again. This technology was later commercialized under the name Outlast, becoming one of the space-certified innovations recognized by the Space Foundation. It is now integrated into mattress toppers, pillows, and specialized clothing used in off-grid environments. Phase change materials function as a thermal energy storage system that requires no electrical input. PCM packs calibrated to melt at approximately 70 to 75 degrees Fahrenheit, or 21 to 24 degrees Celsius, can be cooled outdoors during nighttime conditions, and then used during daytime environments. They absorb heat over extended periods as they gradually melt. Even frozen water operates under the same principle. 1 kilogram of ice absorbs roughly 334,000 joules of thermal energy during melting, enough to noticeably cool a small sleeping space, requiring only freezing beforehand. The sixth method originates from 1963 at Los Alamos National Laboratory, developed by physicist George Grover. It is now deployed on nearly every satellite in orbit. This system is known as the heat pipe and is considered one of the most efficient thermal transfer devices ever created. A heat pipe is a sealed tube containing a small quantity of working fluid and an internal wick structure. At the heated end, the fluid evaporates and absorbs thermal energy. The vapor then travels to the cooler section, where it condenses and releases heat. The wick returns the liquid to the hot end through capillary action, allowing the cycle to continue continuously without external power or mechanical pumps. A heat pipe can transfer thermal energy hundreds of times more efficiently than a solid copper rod of equivalent size. This technology is already widely distributed. Many laptops and desktop computers incorporate heat pipes for processor cooling, making them a readily available source of components. CPU cooling assemblies with integrated copper heat pipes are commonly sold for $10 to $20. Off-grid users apply them for thermal management in solar battery enclosures, compost-heated spaces, and compact systems that require heat transfer to cooler ground or nighttime air without electricity. This 1963 space innovation operates silently, continuously moving heat from one zone to another. The seventh method was engineered for the most extreme thermal environment faced by humans, the lunar surface. During Apollo missions, astronauts working in direct sunlight on the moon experienced suit surface temperatures near 250 degrees Fahrenheit, or 121 degrees Celsius, with no atmospheric medium to dissipate heat. Sweating provided no cooling benefit inside sealed suits. NASA engineers addressed the issue directly at the body level by developing the liquid cooling garment. This system consists of a close-fitting underlayer embedded with approximately 300 feet, or 91 meters, of thin plastic tubing. Cool water circulates through the tubing, absorbing heat directly from the astronaut's skin and transporting it to a backpack unit where it is rejected into space. Water transfers heat approximately 25 times more effectively than air, making direct liquid contact a highly efficient cooling method. This system has since transitioned into civilian use. Liquid cooling vests derived from Apollo designs are now used by race car drivers, explosive ordnance disposal teams, surgeons, and individuals with multiple sclerosis who have impaired temperature regulation. Commercial versions typically cost several $100s, but a simplified configuration can be assembled at low cost. It uses a 12-volt aquarium pump, food-grade vinyl tubing arranged across a mesh vest, and a small cooler filled with ice water. The total cost is approximately $40. The system can be powered by a portable battery pack or a small solar panel, replicating the same cooling principle that supported astronauts on the lunar surface. Users operating in extreme heat report that direct body cooling feels more intense than ambient air conditioning, while consuming less energy than a single light bulb. Stay with me for the next section. Do you like this personality? Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.